The beginning, JWST, and the expansion puzzle beyond the beginning. We are taking a new look at the universe. For decades, humanity has wondered, where did everything come from? How did space, time, matter, and energy begin? And how has the universe changed since that first spark of creation? For nearly a century, the Big Bang theory has provided our best answer. It suggests that the universe began around 13.8 billion years ago. In that moment, all of space was compressed into an unimaginably dense and hot state. From that fiery beginning, space itself began to stretch outward. And with each passing second, the cosmos grew larger and cooler. From that expansion, galaxies would one day form. From galaxies, stars would ignite. And from stars, planets would take shape. Everything we see around us, all of it traces back to that one cosmic beginning. And yet, the expansion never stopped. Even today, galaxies are drifting farther and farther apart. The very fabric of space-time is stretching beneath our feet. To measure this expansion, astronomers use a special number, the Hubble Constant. It tells us how fast galaxies are receding from one another. It tells us how quickly the universe is growing at this very moment. But here lies a puzzle. The numbers don't agree. The story of expansion may not be as simple as we once thought. That is where a new tool enters the picture. A telescope unlike any before it. The James Webb Space Telescope, JWST. Launched in December 2021, JWST is the most advanced eye humanity has ever opened to the cosmos. It represents decades of engineering, collaboration, and imagination. It is not just a telescope, it is a time machine. A machine capable of looking back billions of years, almost to the moment when the first stars were born. Its mirror is a marvel of design. 6.5 meters wide, made of 18 hexagonal segments, each coated in gold. This enormous surface gathers more light than the Hubble Space Telescope ever could. And more light means seeing farther. More light means unlocking fainter, older, and more distant secrets. But JWST's true strength lies not only in its size. It lies in how it sees. Unlike Hubble, which observes mainly invisible and ultraviolet light, JWST sees the universe in infrared. Infrared light is invisible to human eyes. But it carries with it the secrets of the hidden universe. Infrared vision allows JWST to pierce through thick clouds of gas and dust. It reveals the cradles where stars are being born. It shows us galaxies that were once hidden from view. And perhaps most importantly, infrared allows us to see the oldest light of all. Because as the universe expands, light from distant galaxies is stretched. The farther the light travels, the more it shifts into longer, redder wavelengths. Eventually, this ancient light slips into the infrared. Light that once blazed brightly in the visible spectrum is now invisible to us. But not to JWST. JWST was designed to capture these faint whispers of the past. Light that has journeyed for billions of years across the universe. Light that carries with it the story of cosmic dawn. The first galaxies. The first stars. The first chapters of everything we know. And already, JWST is rewriting our understanding. It has revealed galaxies that are older, brighter, and more massive than our models predicted. It has shown us that the early universe may not have unfolded the way we thought. But alongside this revolution in observation, an old mystery has deepened. A puzzle that astronomers call the Hubble Tension. The Hubble Tension is a disagreement over the speed of cosmic expansion. Two trusted methods of measurement give two different answers. And no one knows why. The first method is based on nearby stars and supernovae. These cosmic beacons act like standard candles. A Cepheid variable star, for example, pulses in brightness at a steady rhythm. That rhythm reveals its true luminosity. By comparing its true brightness to how bright it appears from Earth, astronomers can calculate its distance. Type Ia supernovae, massive stellar explosions, work in a similar way. Together, These measurements allow scientists to calculate how fast the universe is expanding locally. The second method looks much farther back in time. It studies the cosmic microwave background, CMB. This faint radiation is the afterglow of the Big Bang itself. It is the oldest light we can see, frozen into the universe when it was only 380,000 years old. From this ancient signal, scientists can calculate how fast the universe should be expanding today. But here is the conflict. The two methods don't match. The local measurements suggest the universe is expanding faster. The CMB-based predictions suggest it should be slower. The difference is around 9%. It may sound small, but in cosmology, it is enormous. And despite years of cross-checking, recalculating, and refining, no one has found a mistake. The tension remains. Which means the universe may be trying to tell us something. Perhaps our theories are incomplete. Perhaps unknown physics is shaping the cosmos in ways we do not yet understand. Dark matter, dark energy, and the human connection to solve the Hubble tension, scientists are exploring bold new ideas. Some propose early dark energy, a mysterious burst of energy that briefly sped up expansion long ago. Others suggest hidden particles, such as sterile neutrinos, ghost-like matter that shaped the early universe in ways we cannot yet see. And some even dare to ask, what if Einstein's general relativity, our most trusted theory of gravity, does not hold true across the largest scales of the cosmos? Already, JWST is reshaping expectations. It has revealed galaxies less than 1 billion years after the Big Bang. Yet many of them are surprisingly massive and mature. Far older looking than our models predicted. This challenges our understanding of how galaxies form and grow. It suggests the early universe may have evolved in ways we do not yet understand. But the mysteries do not end there. The universe is not a smooth sea of matter. It is a vast cosmic web. Galaxies are strung together in immense filaments. Enormous clusters form knots in this web. And between them lie immense empty voids. This structure is shaped largely by dark matter. An invisible substance that does not shine or glow. It cannot be seen directly. But it makes its presence known through gravity. It determines how galaxies spin. It bends light through a phenomenon called gravitational lensing. And it leaves faint signatures in the cosmic microwave background. With JWST, scientists can map this cosmic web more clearly than ever before. They can watch how matter clumped together over billions of years. And beyond dark matter lies an even greater mystery: dark energy. Dark energy is forcing the universe to expand faster and faster over time. It makes up nearly 70% of the cosmos. But what is it? Is it a constant property of empty space? A dynamic, changing field? Or something beyond our imagination? Future missions will help search for answers. NASA's Nancy Grace Roman Telescope. ESA's Euclid spacecraft. Together with JWST, they will measure how cosmic expansion has changed over time. They may reveal the true nature of dark energy. Or lead us to something entirely new. But science is not just about answers. It thrives on the unknown. Contradictions and anomalies are not flaws, they are opportunities. Each mystery is a whisper from the universe, saying, "Look closer." And now, we stand on the edge of deeper truths. Perhaps one day, humanity will discover a unified theory of physics. A theory that merges gravity with quantum forces. A theory that explains time, space, and reality itself. Such a theory might even reveal hidden dimensions. Or explain what lies inside a black hole, a singularity, or perhaps a bridge to another universe. But beyond equations, beyond telescopes and detectors, there is something even more profound. We are not separate from the universe we study. We are part of it. Every atom in our bodies was forged in ancient stars. Every molecule we breathe once drifted through cosmic clouds. We are stardust that has learned to wonder. We are the universe looking back at itself. And with each question we answer, a dozen more emerge. What is dark energy? Do parallel universes exist beyond our horizon? Could life take forms we cannot imagine? What lies beyond the edge of a black hole? Are we part of a multiverse, a grand cycle, or even a cosmic simulation? These questions are no longer just science fiction. They are the frontier of physics and cosmology. And we are standing at the threshold. So this is your invitation. Whether you are a scientist or a student, a dreamer or a stargazer, join the journey. Together, let us travel beyond stars, across nebulae, into black holes, and into the quantum realm. Because every time we look up at the night sky, we are not only stargazing. We are searching for meaning. We are listening for echoes. We are reaching for our cosmic roots. And maybe, in the silence between the stars, we will discover a reflection of ourselves. Not just as humans on Earth, but as participants in an unfolding cosmic symphony. So until the next discovery arrives, until the next light crosses billions of years to reach us, keep asking, keep wondering.